Thank you very much for the introduction, for inviting me here. It's very nice to be able to participate and also to see in person. The work I'm presenting today is a research project I've been very interested in the last couple of years. This is about developing new semantic foundations for machine learning, which are informed by methodologies from logic, algebra, and category theory. Most notably, as we will see, this notion of lens plays a big role. I should also mention this is work I've done in collaboration with other people, in particular Jeff Crackwell, Bruno Gavranovic, Neil Gani, and my student in London, Paul Wilson. So the main drive, the main inspiration from this work comes from an area which is my background, and I suppose the background of many of you as well, which is the area of programming language theory. As computer scientists, we are usually interested in providing methodologies to reason about programs in a formal manner. A major field in this respect is the field of formal verification, where we are interested in giving mathematical proofs that certain properties of a program hold. For instance, that a program is correct, that a program terminates, and so on. Now, what I claim is that in order to be able to answer this kind of question, which, especially for the outsider, I would say are among the most pressing ones, we actually do need some firm foundation for what concerns the meaning of program, which means we should be able to rest on a well-thought, well-pondered formal semantics. Indeed, many times I believe the life or death of formal tools depends also on the language they choose, the formalism. They need to pick the right level of abstraction, they need to pick the right primitives to reason about programs. And this choice this choice is usually very important in determining how the tool works. So this is why I here highlighted what I believe is this kind of virtuous circle in which, in order to do verification, we need semantics. And similarly, as we will see in machine learning, in order to get to the goal of verifying neural networks, which is a topic I will get at the very end, we'll need first to rest on firm semantic foundations. So this idea of exporting the paradigm of semantics to other fields is not new. It's something myself have been very much interested in working on in the last few years. Here, for instance, there are a few examples of theories of languages that me and other people have tackled using this kind of methodology. The idea is always the same. The idea is to pretend these formalisms are programming languages and try to come up with appropriate semantics for them. Now, as I mentioned here, it's not just a matter of giving them an appropriate semantics, it's also a matter of giving them the proper syntax. In the context of programming languages, we usually know what the syntax is, but as you can see here, in these other formalisms, usually the formalism is just some kind of graph. It's a combinatorial structure. So we want somehow to be able to reason about this combinatorial structure in a syntactic way. So finding the right primitives in this context means finding both a proper syntax and semantics. This obviously will come back in the context of machine learning when we deal with structures which are often graphical, like neural networks of all kinds. So this is something that I wanted to highlight and we should keep in mind. Now, coming to machine learning, of course, the landscape is very rich and diverse. I mentioned neural networks, but there are obviously many different kinds of neural networks that are trained in many different ways for many different tasks. So suppose we make sense of this. What is the end goal we have for tackling this such big field? I would say there are four pillars here, four aspects that we want to keep in mind that will determine whether our foundation is what we are looking for. So there are two that are, let's say, common to all these kind of enterprises, which is striking for uniformity. I already mentioned there are many different kinds of learning. Here you can see some deep neural network, some reinforcement learning, some recurrent neural network, some convolutional neural network. We want to be able to reason about this language, these formalisms within the same mathematical language, in order to be able to highlight their differences, their similarities, to compare their expressiveness. A second important point is simplicity. People program with these structures, and I believe a mathematical language should be able to inform the way people design and specify these kind of structures. This is connected with the quest of finding the right primitives that I was mentioning before. If you're able to find the right primitives, the right level of abstraction, hopefully we can provide people with something attractive when it comes to program with these networks. The last two items are more specific of the field of machine learning. They're probably words that you have heard before. They're very popular needs that people write in their grants nowadays. First one is explainability. Explainability addresses a major issue, a major concern that especially policymakers and also general public has with machine learning. Machine learning algorithms surround us, and they are more and more impactful in our lives. Imagine you want to be given a mortgage. You go in front, you sit in front of an agent of the bank, and the agent will insert your data, will run something, and will say, no, your mortgage application has been refused. And you ask why? They will say, well, the computer told me so. No, that's usually what we answer all the day. And also when we bring some customer service, they say, oh, the system said so. So the problem with a big issue that people have with machine learning is that these systems are often deemed to be black boxes. We train them to reach certain conclusions, but more often than not, we are not provided with many insights on how they reach certain conclusions, what kind of evidence they examine, and so on. So this is the issue of explainability. There are, of course, many approaches to explainability. I believe semantics, for once, can give us many insights on how to make these structures more explainable by somehow highlighting what is their internal structure, their internal functioning, give us a way to describe their behavior in a more expressive manner than what we have currently available. Connected to that, there is the issue of trustworthiness, which obviously comes out, is related to explainability. Namely, we want to make sure a certain algorithm works as intended. And this, of course, comes out more in critical applications that have to do with safety, healthcare, for instance, or defense. And this brings us all the way to verification. No? So we want to verify some properties of the neural networks in order to increase our level of trust in the decisions they make. And once again, I believe semantics can provide a good lead in answering these kind of questions. So these are a bit, let's say, 4 directions in which this kind of foundation can help with. Now, after all these premises, let me finally get to the actual approach we are suggesting. Because machine learning is so vast, we have to focus, in order to give you a convincing case study, to something simpler. And we take what I think is perhaps the most ubiquitous machine learning algorithm, which is gradient-based learning. This is an example of gradient-based learning. What happens here is we have a neural network. For now, we don't care much about the architecture. We just say the network is a bunch of nodes with arcs among them. The arcs carries weight, called parameters. This network is computing a function determined by the parameters. So it's mapping inputs to outputs. In particular, this neural network is analyzing, is processing some image, and is aimed at recognizing what kind of animal is in the image. Now, the prediction, as you see, may be not as accurate. However, the training process is supposed to make it better. The way it works is this prediction is fed into what we usually call a loss map. The loss map is a function that compares this prediction with the actual label that should have been given to the image. In this case, that the image is actually a cat. Notice that the label is provided to us when the learning is supervised. So this is the case we're covering here. The loss map so compares these two information and backpropagates the information of how much the error was. This information is then used to update the parameters of the network in order to improve their accuracy. There is a middleman here, which we call the optimizer, which is essentially the algorithm we use to update the parameters. And this is usually where the gradients are computing. So this is where gradient descent intervene, and this is why it's called gradient-based learning. There is yet another component at stake in this picture, which is the learning rate. The learning rate intuitively is a factor that tells us how drastically we should try to improve the network. Okay, at what pace we should try to make it more accurate at each iteration. So this is basically the picture we now want to analyze. When I was exposed first to this picture as someone coming from a different area, I had many concerns. Now, it looks like here there are many moving parts that are expressed with different mathematics. No? The mathematics that we use to express neural networks is not the same that people typically use to describe the optimizer. Essentially, all these things live together, but not in a very coherent way. So I was wondering, can we give mathematical meaning to this picture in which all these parts are accounted for in a bit more systematic and uniform manner? Also because I should mention, whenever here you read optimizer, for instance, that's not a single thing. People study lots of different optimization algorithms. They have names such as momentum, Nestron momentum, Adam, Adagrad. So really, in each of these components, there are many choices that can be made, and we want to make sure we understand the choice we are making and how it interacts with the other parts. So all this is why we want to give a semantics at a deeper level. This is why we want to give some insight on what are the fundamental mathematical structures that underpin this picture. This is usually the quest we face in many fields. You may think about concurrency, how much people there try to figure out the correct primitives, the correct basic notion. Here we want to face a similar challenge. So now I'm going to tell you how we do it, how we want to make it. So what is our proposal for these fundamental structures? At the end of the day, throughout the slide, throughout the presentation, this picture will become this picture. Now you may think these are two pictures, no, we didn't make any progress. But as a matter of fact, these two pictures are fundamentally different. The one on the left is simply a funny picture I drew for you. It doesn't carry any formal meaning. The one on the right is what we call a string diagram, and this is a completely formal mathematical object. It can be thought as a graph where we have these boxes connected by wires. At the same time, it has a dual nature. It can be thought as a term. This is a term of a syntax. It will be a graphical syntax, okay, especially in this respect. So this is something not everybody is used to, because usually we reason about one-dimensional syntax when we only compose things in sequence. This is a graphical syntax where we can compose things in sequence and in parallel. This is what string diagrams are for. I will explain later why we choose string diagrams. For now, let's just keep in mind, this is both a graph as the original objects we intend to model. At the same time, it's a completely formal term coming from some syntax. So we can reason about it by inductionist, compositional, and so on. So this is the, let's say, end goal, transforming this into that. What are these boxes? So these boxes are going to be our plain primitive notion, is something which we will call lenses, most notably parametric lenses. So parametric lens is the unit that we use to reduce all components of learning. What I would say is the most surprising thing that we found along the way in trying to do this is that this notion of lens does not only model specific parts of this picture, doesn't only model, for instance, the neural network, is actually capable of modeling the optimizer. The optimizer itself is a lens, the loss map is a lens, the learning rate is a lens. So all these components that were seemingly diverse at the beginning, it turns out they all are parametric lenses. Moreover, the way they interact in this picture, the way they interact in training the network, can be completely reduced into the notion of lens composition. So lens composition in this picture is simply when we put two lenses next to the other and we plug them. Here is very high level. We don't really see how this plugging is computed, but obviously it gives rise to some kind of operation that is made there, which is lens composition. It turns out the learning that is happening here is simply lens composition of these lenses, informing a bigger lens. Okay, so this is really the picture now we are striking for, what we want to get to. And in order to do so, I will now proceed in steps. First of all, introducing and motivating parametric lenses and why they are good at modeling these various components and their composition. Okay. So, parametric lenses are the union of two notions: a parametric map with a lens structure. A parametric map is simply a function f from A to B that also takes values from a set of parameters p. I say a set, I should say a space, but let's say for now is a set, and this you can think of, if you like, as a function from pairs of a parameter and an input into an output. These things, they do form a category, obviously, which we usually notate as par of C. C is where the function f from A to B comes from, and in par of C, this function always carry a parameter. You see, this is a first instance that already makes us see how string diagrams are particularly useful and effective in highlighting these interplays of inputs and parameters in a way which I would say standard syntax wouldn't make it so clear. Because you see, we can really see in composition and reparameterization the different role played by inputs and parameters. So in this notation, inputs and parameters, they simply participate more or less the same with the same role in the domain of the function. In composition, you see clearly that the composition is along the codomain of the first function and the domain of the second one, and the parameter space is enlarged. That's what's happening in composition. Reparameterization is instead an operation which is specific of parametric function, in which what we do is to change the parameter space using yet another morphism from Q to P, to change it into something parameterized in Q. So these are parametric maps, and an obvious example of a parametric map is a neural network. We already said that neural networks have parameters, so this should suggest us what's going on here. The category in which these parametric maps live is smooth. Smooth is the category where morphisms are differentiable functions between real numbers, okay, between vectors of real numbers. This is, for instance, how a neural network would look like as a parametric map. This is the space of the inputs, the space of the outputs. These are the parameters, which are not just the weights, they are also the biases, which contributes to the nonlinear part of the computation. This picture now is quite coarse. It doesn't account for the internal structure of the network. However, even though I'm not going to go there in this talk, be aware that we can make this way more specific and enlightening how the network actually looks like in the inside. A first approximation of this is, for instance, that we can describe as a parametric map the network in a layer-wise manner. So layer 1 becomes a parametric map, layer 2 becomes another one, and their composite gives us the bigger network. Okay? So this is the first reason why we obviously want parameters around. We're motivated by the example of neural networks. Why we want the lens structure around? The lens structure intuitively is going to account for this backpropagation process that happens in training. So lens structures capture the idea that neural networks do not only experience a forward flow of information, but are capable of receiving a backward flow of information in order to update their own structure. That's a bit the general idea. More formally, a lens is something that has this shape. So a lens goes from an A and A prime and a B and a B prime. It consists, is a data structure that consists of two operations. A get operation going from A to B, and this is called the forward part of the lens. This you can see as your function, for instance, your function from A to B. The put you can think of as the reverse mode of your function. Is the reverse mode because it takes an input, it takes something we can think of as the change that we want to see in the output, and it tells you what changes should impose in the input in order to get that. So this is also why I picked this notation, because I want to highlight to you that in general terms, A and A prime are completely distinct variables, but typically there is a link to them, namely we can think of A prime as changes in A. Okay, this is the terminology I use now to describe this. And once you think of this B prime as change in B and A prime as change in A, it becomes clear also what typically this put map would be. It will update the way the function works by looking at what kind of change we want to see in the output. Now, this is the one at the top. Is the way we could describe this with string diagrams. You see simply the lens with A prime on the left and B prime on the right. That's not very insightful, obviously, because we want to be able to access the operations that are inside the lens. And that's why we can have this other notation where we somehow open the box of the lens and we have the get map and the put map clearly displayed. Now, maybe I'm not sure if that's visible enough, but something else you should notice here is that unlike the string diagrams we have seen so far, in these string diagrams here, there is a directionality. So this A, the information is flowing towards the get and is getting out. At the same time, from the A, the information is going back into the put together with the information from this B prime, and this put is sending back some information on A prime. So the reason we have this information flow now is because we really want to highlight that the get is the forward mode and the put is the reverse mode of the lens. So this is something that will become very useful. And once again, it's something that if we didn't use this kind of graphical syntax, if we just use some kind of textual syntax, I would say that this would be much harder to see at glance. Let me open a parenthesis on how do we open this box. You may think I'm making this up, no? Because so far we know string diagrams are this kind of thing. This kind of look like something that we can translate into a term. So how is this a string diagram? How this is a formal object and not just some picture I'm making up? Well, there is a mathematical reason for that. Namely, we are not now using string diagrams in lens of C directly. So I should also have mentioned that these lenses on the base category C, they form a category where the lenses themselves they are the morphisms, and we are not using string diagrams directly in lenses when we open the box. we are looking at a bigger category that has more expressivity. We're looking at a category usually called the category of Tambara models over C. Why we're allowed to do that? Because Tambara models, it turns out, they are the same as precious over lenses. Okay. This doesn't mean anything to you, just switch off for a moment. But I think this is interesting for those of you that are into precious, for instance. It turns out the category precious of lenses is some other kind of known object, something having to do with profunctors. And it turns out in this category, we have a much richer string diagrammatic language which we can cheat and use to speak directly about lenses. Why can we do so? Because obviously lenses, as any category, has an embedding into its own category of precious. So we can use this embedding to look at the image of it, and we will get string diagrams like this one that talk about the original category. So they talk about lenses. So that's how we can do it. Okay, now let's put the category theory aside again. And let's get back to our leading example. As I already anticipated in various forms, lenses provide a way of expressing the fact that neural networks have a reverse mode. So neural networks are lenses in the categories mode that you already encountered. How is that so? Well, f here is the function that the neural network is computing from an input A to output B. And R here is the reverse derivative of f. So the reverse derivative is taking an input, is taking a change in the output, and is telling me, is giving me a linear approximation on how much I should change the input in order to get to that output via f. Okay? This is the usual intuition about the reverse derivatives. In more formal terms, here this notation means this is just the Jacobian matrix for the partial derivatives of f with respect to x, and this is how I compute what I just described in words. There is an interesting aspect here to highlight, namely the way we account for this reverse derivative in categorical terms is not something we came up by ourselves. It rests on this idea of reverse derivative categories, which is this attempt of axiomatizing the notion of derivative in a categorical manner. Well, it turns out this structure is just what we need in this case. We have that whenever we have a reverse derivative category, we can give rise to a category of lenses in this manner, where the reverse derivative gives you the put part. And this in particular applies to neural network. But as we will see later, this also applies to other reverse derivative category of interest that we can then learn in the same manner now that we learn neural networks. Okay, so we have seen parametric maps, we have seen lenses. Now parametric lenses are simply the clever composite of these two notions. So they're parametric maps with lens structures. Formally, what I'm doing is to form a category para-lens of C. This is how string diagrams look like from the outer. Obviously, I can always access the box as we said before. Then we have composition and reparameterization the same manner as we had with parametric maps. Obviously, now there is much more interplay now because in the composition, I will also do some lens composition internally. So now you may wonder, how does this picture now look for neural networks? Now we said neural networks are parametric maps, they are lenses. How does it look when we account for them as parametric lenses? So this is what they look like. F is the function that the neural network is computing. This function you see is receiving values from A, it's giving me some B, but it's also dependent on the parameters of the network. There is a second gadget inside the neural network, which is the gadget that is computing the reverse derivatives. What is this type? Well, you see there is A is coming in, B prime is coming in, and parameters P coming in as well. And this is giving me back a change in A and a change in P prime. Now, you know, in training, what we're interested in is in this. We want to change the parameters along the way. So what the interesting bit of this computation will really be what the P prime does, what the P prime look like. The change in the input looks odder. It's not something we generally want. So in standard learning, we are going to discard it. But we will see later actually it becomes useful in other ways. So just bear with me. For now, accept the fact that this has this type. It turns out this type is not a bug, it's going to be a feature. Something else I want to mention is, as before, this is kind of a higher level view of the network, but with parametric classes, we can really account more for the internal structure. For instance, we can account for a single layer of a neural network by composing together parametric classes that interpret the specific part that compose a layer, the linear part, the bias, and the activation layer. These all can be formalized as individual lenses, and the composite gives you a layer, composite of layers gives you a network. So this is the high-level view, but there is always also available a more fine-grained view, which will be useful in some other kind of analysis. All right, so this is the picture we started with. We got here, okay? So we saw how the neural network can be a parametric lens. Now it's time to look at the other components of learning, okay? Let's focus in particular on the optimizer, which I find is perhaps one of the most surprising here things that actually happen to work when you regard of it in terms of lens and lens composition. So the most basic kind of optimizer is simply basic gradient descent. Basic gradient descent is the optimizer that simply updates our parameters by using reverse derivatives, okay, by the gradient descent algorithm. It turns out basic gradient descent is a lens of this type. You have to look at it rotated by 90 degrees. So it's a lens from PP to PP prime. Okay, and these are the get and the put map. So the get is simply the identity. The put map is simply making the addition. So you may ask, where are the gradients here? Well, it turns out in this approach, the gradients are not anymore in here. This only gives us kind of the logical structure of what we're doing. The actual computational structure is now hidden in the model. So this is going to just tell me what I do with this. Oh, did I do wrong in touching it? Should I try to make it bigger again? Okay, maybe I will just leave it like this. Okay, I hope you can still see right now. So as I was saying, the reverse derivatives are not anymore in the basic gradient descent, as it usually is the case. They are now in the model, and the way they're intervening in the computation will be via this exchange. So what is this exchange? This exchange, you can regard it as lens composition, but really, if you regard this and this as parametric lenses, this is simply what we had before as reparametrization. So if you remember, reparametrization meant to plug in something here, a morphism that changes the parameters of my lens. And in this case, what changes is the lens that gives me basically the descent. Now, this wouldn't be as exciting if more complicated kinds of gradient descent algorithms didn't work just as well. This is the kind of uniformity that we were looking for. It turns out many of these are captured. Actually, it's not like we found one that cannot be captured. We just stopped searching at a certain point, but we made a good progress in showing that many of those that are considered, let's say, the main ones, like optimizers such as Adagrad, Adam, Nestro, Momentum, and so on, they can all be accounted of in the very same way. They are just other kind of reparametrizations on the original network. They're going to be more complicated than basic gradient descent, as you should be. Basic gradient descent is stateless, simply does identity addition as a lens. This is, for instance, how Nestro momentum looks like. You see now it's stateful. The computation depends on some state S. The get map is not anymore. The identity depends on some parameter gamma. And the put map is also something more complicated that depends on the previous iteration of the process. So, but the message here is not really like how this formula is written, is really in the fact that all these other optimizers, it turns out they all are also lenses, which gives us evidence that this notion is robust and useful for our purposes. Okay, so we're seeing optimizers and models. Now let's have a walk for loss maps and learning rates. This turns out they are also other kind of lenses. This is, for instance, the mean square error lens. The mean square error map is a typical one that is used. This is the strain diagram that show how it looks like as a parametric lens. This is a learning rate. Imagine your learning rate is usually a factor you multiply with to amplify your error. This is, for instance, the factor is eta. This is how the lens for the learning rate look like. You see that it's trivialized in some way. This dot here means we discard what's coming in here, and simply this here we're multiplying this for this other value. If we simplify this picture, because obviously we have equational rules that work for lenses, this is one reason to use them, we get here. And when we get here, we see really how we recognize the usual computation that the loss map does. The loss map is taking the true labels, like the information that the picture should really be a cat, is making a subtraction of that, or is making a comparison, which in this case is a subtraction of the true label with respect to the label that was computed, and is amplifying this by some factor eta. Okay, so in simplifying the previous picture, we really see how the computation goes in the way we expect. Okay, so this is how the single ones, the single components look like as lenses. Now I want to spend some word on how they all participate together. Now currently we are focused on individual parts of the learning, but we have claimed that the whole picture here, which is a lens because it's a composite of many little lenses, models learning. So how does that happen? First of all, the big thing here is a parametric lens, but of a kind of a trivial type. So you notice that in here there is no input, here there is no output. So really the type here is just what is here, the final objects, which is string diagrams here amounts to not doing any work. So how do the inputs, output, and parameters intervene? Well, in this picture, they are all coded as parameters of the parametric lens. So this is a parametric lens of this type, and the parameter space, as you can see, is quite rich. It includes A times P times B, where A is inputs, P is parameters, B is outputs, and changes in those things. Graphically, as you can see, the A's, the P's, the B's, they're all coming from above. The reason why I showed you this type is because it's now we can say what is the put map of this lens. Remember, a lens has a get map and a put map. The get map in this case is trivial, but the put map is really what is doing all the work. So if we make the computation, this is how the put map has type for this lens. So you see that the put map will take inputs, outputs, parameters, and give me changing inputs, changing outputs, changing parameters. So how do we make sense of this type in the context of learning? Well, what you have to think about is that these A and B's are like my data set. Now, when I receive a data set, I receive pairs of inputs and outputs, which are like how the function is supposed to work. I have the current parameters. What I should do is to update the parameters. So this is really what this put map is doing. It's a bit deceiving because I'm not just receiving the P prime, I'm receiving also changes in A and B. But if you look at the picture here, they are discarded. So you see this B prime here is going to a dot, the A prime here is going to a dot. So these ones I don't care, but the P prime is what I care. If you go even more inside it, in the put map, you see this is how it works. So it starts with inputs of A of type A, BT of type B, and parameters P, giving me this A prime, P prime, B prime, T composers that are computed as follows. So the BP is the value that I get when I use my function f. F, remember, is the function that the model is computing, and apply to P and A, so the current parameters and current inputs. This gives me some BP. Then I use this BP here. I compare it with the BT. So these are this is the actual answer that I should have received, and I feed this into the loss map. Okay, and I amplify this by alpha. Alpha is the learning rate inside here, and then I feed this into the reverse derivative of the loss map. This gives me new values that are changes in BT and BP. I don't care about both of them, but I care about the change in BP. Oh, I magically didn't get that bigger. I care about the change in BP because this is what I now feed in the reverse derivative of f. So the reverse derivative of the model is going to take PA and this value that I computed, the change in B prime, in B, and is giving me the change in parameters and inputs. And this P prime is what eventually is going into the optimizer. So I went through the hoops here because I really wanted to give you evidence of the fact that even though this looks like a high-level picture, and you may wonder, okay, this is like a clever trick, but it's not really doing anything. Well, it does do stuff, but it just hides it very well. Okay, this is not something we invented. This is not something we define ourselves and have to check this through. This is just the result of computing what composition of lenses look like. I have to be careful. I'm not used to TVs responding to my touches, no? So I shouldn't touch it. Okay, is this clear enough, at least on a high level? So now we have this put map, and we say, the put map of this lens is how training works. Obviously, this is just one step, though. No. What usually happens is we process many different input-output pairs in order to improve in our training process. So this is how this will look like in the diagram. You see the put map is used many times, is iterated as many times as you like. Something interesting to notice is that in this perspective, the rows become switched. Maybe the parameters are what matters. The parameters become my input-outputs, and the data set become the parameters. But in a sense, this is what happens in real life too, no? In a sense, the data set, the inputs and the outputs now become my parameters. Really, what I want to change are what originally were the parameters of the network. So I think it only makes sense that the roles are switched also in the formalization. Okay, so let's say we figure that out. At least at a high level, how this all works. So the reason to do this, obviously, is not just to say basic gradient descent works this way or optimizer algebras works this way. Now that we have a categorical understanding of it, we can really try to exploit it at its full potential and see, for instance, how would this work in other categories, or how would this work if we just change a bit all the parameters that we have in our picture. The first variation that we explore is what is called in the literature deep dreaming. Deep dreaming in the literature, machine learning literature, means the act of taking a neural network that has already been trained and see how it, supposing, for instance, in this case, your network has been trained to recognize dogs in the picture, and then we let it modify the input picture, over-process it, depending on what the network has been trained to recognize. So, for instance, in this particular example, the input image is some jellyfishes, but the network has been trained to recognize dogs. So if we let it act freely on the image, it will morph the jellyfishes into some psychedelic dogs. Okay. I mean, this is something studied. I believe it has some relevance. But what I'm interested in here is saying how this enters the picture in our case, because this answers a question we had before. So something about the above picture here, the parameter learning, was that we don't really do anything with the change in A, change in B that we discard. Well, it turns out these things are still useful to have around, because now that we have them, we can account from the difference between parameter learning, so the standard one, and deep dreaming in a very concise way. In deep dreaming, what changes is that the network has been already trained. So the P primes are not of any use anymore, and we discard them. The optimizer now does not reparameterize anymore the model, it reparameterizes the space of the inputs. So you see that now the A prime, the change that we want in the inputs, is not anymore discarded, it actually participates in the optimizer and is going to change the inputs at the next step. This also shows you how I believe this picture is effective as a design device. Now imagine you are a developer that wants to design a training protocol. If I want to switch from parameter learning to input learning, I just take the box and I shift it. Okay, so this is really a high-level view that I can take on this kind of design, which I think can be an interesting perspective to explore. So the second variation I want to mention is the learning of other models. We said that this picture of learning works in smooth. That's how our main example comes out, learning real value neural networks. Nothing prevents us to see how those generic assumptions work in other categories. A category in which the assumptions that we need work is a category of Boolean functions. And the operational model we can look at now is the model of Boolean circuits. Okay, so a circuit with gates, usually AND, OR, XOR gates, where bits 0 and 1s flow in and out. So it turns out the category of Boolean circuits can be trained just as we train neural networks. So we can draw exactly the same picture as we did for neural networks in the category Bool. You see that now we just replace the neural network with a Boolean model, a Boolean circuit. I put here 0, 2 just because to give you the idea that here now the values that are flowing in and out are Boolean values. And we can train it by basic gradient descent. And this is actually something we studied in a paper. We can actually train in a meaningful way a Boolean circuit. And we can train to recognize some data sets. For instance, we tested this on MIST. Some other kind of data set people usually take to show how they design these algorithms and their networks. And something I want to highlight also from a mathematical viewpoint, which I find interesting, is that the reverse derivative, which in the case of neural networks was defined somehow by hand, just because we know how reverse derivative for real functions work. In the Boolean case, they can be defined inductively. So R of F will be a string diagram that I can define inductively using the grammar of string diagrams that define Boolean circuits. So if you're familiar with the word of Yves Lafont, for instance, you know that there is all this school of French people working for instance, in describing different classes of circuits, most notably Boolean circuits. So this is really Lafont's syntax for Boolean circuit that here we can take as it is, and we can define a reverse derivative of F inductively. I think this opens also some interesting avenue for a more efficient computation of these reverse derivatives, because we do it inductively means we do it in a compositional manner. So hopefully it can become more scalable. Also, this computation, which as you can imagine is a very expensive part of the process. Okay, so I gave you a glimpse also of these Boolean circuits and how they work, how we can now train other classes of models that are not neural network. And now I want to come back to the bigger picture and just make a little summary of what we learn on the way. Oh, I think I will have some water. So this is the picture that summarizes it all. We started from some generic sketch of how things should work. We turned it into a fully formal mathematical object. These provided the semantics in terms of lenses of gradient-based learning. Now, what are the properties, the virtues that I think we wanted to seek, and I think we achieved at least to a good extent? First of all, uniformity. Now, all components that are at work in the learning process, they reduce to a single concept, which we identify, this concept of parametric lens. This concept also carries some abstraction with it. We understand that from that level, that perspective, optimizers, model, loss maps, and not just the basic one, but like different kinds of them, they all are subsumed by this more general concept. They all become instances of the network and can be now compared in various ways. Another point I want to make is about compositionality. Obviously, I would say that the field of machine learning is not compositional in the same way as we say compositional. They are worried about compositionality. They're interested in it, in the sense, for instance, of making computations layer-wise. Here we have a much more flexible, I would say, form of compositionality, in that these various components, they are all now lenses. We can plug them at will. We can make things such as train an optimizer. So the optimizer is a lens, so it can go here. We can train the optimizer. It's something people do in meta learning, for instance. We can compose together a model that has been trained with one which is untrained. We can compose together loss maps. For instance, we can form Nestor momentum by composing together Nestor and momentum. We can do all these kind of things that I would say is not immediately obvious how to do in a more lower level formalism. Hopefully, they also open some design space that is yet to be explored. Another point I want to highlight is we could have made all this with your favorite logic. We could have used some kind of one-dimensional notation. We choose to do it with string diagrams. I think there were good reasons to do this. The main one that I like is that the formalism is completely resource sensitive, because we have this graphical shape always in place. It really gives us the idea of how information is flowing at any time inside our learning process. When I started to study this, I was staring at these manuals on machine learning, these tutorials with all these formulas. I don't think they were as clear to me, at least, as this picture is on what is going on in gradient descent learning. In this picture, you clearly see how in the algorithm, the various parts that contribute to it exchange information with one another. So I think this carries also some kind of pedagogical value on how all this machinery works. So going forward, there are of course many things that can be explored. There are a few ones that I'm currently interested in, and I care particularly. Obviously, there are many kind of models to be explored: convolutional neural networks, recurrent neural networks, adversarial networks. I can tell you many of these work in this lens perspective. Some of this has been explored. For others, we didn't do it, but we have an idea of how they should work. There is a particular kind of model that I'm interested in, which are simpler models of neural networks. I already mentioned one of the simpler models, Boolean circuits. So people are interested in Boolean circuits in machine learning to the extent to which they provide a more performant model of the trained neural network. Something that is studied is something called quantization or binarization, in which a neural network has been trained to be accurate. It is not as performant. So what you do is to discretize it. Now, instead of having real values in the weights, it's just 0 ones. So you get a Boolean circuit which computes the same function in a sense. It will be a bit less accurate, you see, but it will be much more performant, because obviously now it works with 0 ones instead of real numbers. And most importantly, this concern also arises when you want to implement neural networks, because our computers, they're not made to handle real numbers, real values, no? So there is always the big question on how we approximate real value computation. And one of the answers is using these discretization processes. So So I mention all this because this is some real concern that machine learning community has about binarization, and I think we can say something interesting here. Something that we already do in our framework is we demonstrate how you don't need to train and then binarize. You can directly train here, and this can be done in a meaningful way. So this is something new, the training done directly on Boolean circuits. Something else I would like to explore is other kind of semirings. Boolean circuit is just specific semiring. We had a follow-up paper to the one exploring the Boolean circuit, in which we show that other kind of semirings also offer us a platform for training. So we can, in particular, train circuits over the polynomial semiring. And this is interesting because this intuitively gives you a more balanced trade-off between performances and accuracy. It's not as performant as the Boolean circuit one, but still is better than the neural network. At the same time, I believe it's going to be closer to this in terms of accuracy than the Boolean model is. So it's kind of a compromise, it's kind of a middle ground that I believe can be interesting. And our theory makes it available to people to study. So this is something I would like to study next. In particular, a form of arithmetic called theoretic arithmetic, which can be done using a certain semiring, which essentially truncates operation. It's like modular arithmetic where we truncate operations instead of going back to the start. So this is one direction. Then, of course, many of you are into program mathematics or program construction. So can we do some nice programming with these lenses? I believe so. I mean, I didn't mention this, but I think many of you may know lenses because of functional programming, for instance. Now there are libraries. There is an Haskell library for lenses, and maybe also Python one. So lenses are definitely a concept that is already out there. And we do have some prototype implementation of these ideas. The first one is is a Python library that has some lens operations to do machine learning with lenses. Second one is the version for Boolean circuits. I wouldn't say they are ready to be usable for a generic public. They're more like proof of concepts, but still you can have a look and get an impression of how they would look like if they were developed. I just want to also give you a glimpse on how things look like in this library. For instance, this is how we can define a layer of a network. This mimics this feature that we had before, if you remember, with the three lenses. So you see what happens here is that this is composition of lenses. This operation that you see here, this notation. So the network is defined by composing this lens with that lens with that lens. Then if we want to update it, what we do is this apply update, which simply is reparameterization. So we reparameterize dense, which we define here, with basic update, which is this other lens. And then we compose it with the loss function of the learning rate. So you see, I find this quite interesting that also in the programming here, this is training. A training is simply composition, okay, of entities, of lenses in this case. So I believe this is something that can be explored. Is offering a different alternative high-level way of designing neural network algorithms, which I would say is very much akin to functional programming. Okay, so for those of you that are into that, I think this may offer some appeal. Last point I want to mention is coming back full circle to what we mentioned in the beginning, namely with formal verification of neural networks. Specifically, I want to zoom in a specific approach to formal verification of neural networks, which is called continuous verification. This is also, for instance, something that Kat has been working on a lot recently. In continuous verification, the idea is that you want to verify properties of your network step by step, at the same time as training it. Okay. What kind of properties are you typically interested in? Are properties of so-called robustness to adversarial attacks. The idea is that you want to make sure that a small perturbation on the input doesn't determine a huge difference in the output you are getting. Okay? This is the kind of a property that we are interested in verifying here. This property is usually encapsulated in the loss function. So this is how the verifier intervenes in the training. It intervenes in making the loss function rich enough so that it encapsulates the constraint that that we want to impose, okay, the property that we want to ensure. And the argument here is that doing so in the verification process is more effective than doing so at the very end, when the network has been already trained. Now, another piece of theory that has been developed to contribute to this field is there is a whole thread of research on what kind of specification language we should use to describe these loss functions. So these loss functions should express properties that we want to verify, and people came up with meta languages called differential logics that express these properties and then are translated into these loss functions. Now, how do lenses can help here? Well, I think at a higher level, this picture cries for lens modelization. We already know how to explain the training of a neural network as a lens. So what remains to be done essentially is to capture the whole cycle as some form of length proposition, which I think is believable because you see there is a back and forth exchange of information here. Pretty much the same uniqueness every time we are working with lenses. So this could give a uniform single layered language in which we express all this cycle instead of reasoning about it in a more meta-theoretical manner. This would have also the desired consequence of providing us an off-the-shelf specification language for these structural properties. So instead of having these differentiable logics, which act on a meta level in expressing this loss function, now we know that the loss function is itself a lens, so it comes with this rich language that we can now use to specify directly at the same level as this picture leaves, the properties that we want to enforce in the verification process. So these obviously are very preliminary ideas, but this is one direction that we are exploring and also we would like to work on. Okay, so this is everything. And I leave you with some pointers for the implementation. And this is a partial bibliography in case you want to read more about this. Thanks.